So now we want to start afternoon session, evening session in third day. So the first speaker of this session is Hao-Jun Chen. The title of this topic is Error Exponents and Strong Compass for Quantum Software Covering. This is joint work with Li Gao. Please start.
Okay, thank you very much, Hayashi-san. And I would like to thank the organizer for holding this Beyond IID conference. It's the 10th year. Okay, I'm Hao-Jun Chen from National Taiwan University, and this is joint work with Li Gao from the University of Houston, and our paper can be found on arXiv. Okay, let me jump into the problem formulation of quantum soft covering directly. Okay, we consider a classical quantum channel, which takes a classical symbol X to output a density operator on some Hilbert space B. Here, we don't put any assumptions on this Hilbert space B. Okay, given an input distribution, probability distribution Px, and the output state is the average of the density operators. Let's denote this as rho B. But sometimes we don't have the mathematical descriptions of the channel and also the input distributions. So the question we want to ask is, how well can we approximate this rho B at the channel output state induced by the probability in distribution Px by querying to the channel? Meaning that you can pick some X as input and send through the channel, and you'll get some output. But how can you approximate this average state very well? Okay, and a standard approach is to use a random code book, which contains m equiprobable cohorts, and where each cohort is pairwise independently drawn from some probability distribution, say Px. Then we send these cohorts through a channel. So at the channel output, we just make a mixture of those density operators, and we call this the code book induced output is density, rho B sub C. This C is the code book, given the code book, it is a mixture. So given Hm, which is the size of the code book, then we want to ask how close is rho B, this rho B sub C, the code book induced output density, to the desired true marginal density rho B. That's the question we want to ask. And to measure the closeness, we consider the trace distance as the error criterion, which is defined by this. And because this rho B given C is itself a random variable, because we consider random code book, so this C is random, is also a random variable containing m random cohorts. So we would like to take expectation. Then our question becomes that for each code book size m, then how small or how large is the expected trace distance, where this expectation is taken with respect to the random code book. Okay, we call this problem the one-shot quantum soft covering. And by the one-shot, we mean because we do not impose any specific structures on the channel, except for the classical quantum channel. Okay, this is a one-shot setting. Next, let's move on to the memoryless asymptotic setting. Here, we consider the product channel of the classical quantum channels, which takes n length symbols to the tensor product of each density operators. And in the n-shot setting, we consider two cases of the input distributions, because right now the input alphabet is n-fold. The first one is the IID input, so just a tensor product of Px. Then the corresponding output is also just a product state, rho B tensor n. Okay, by sampling from this IID input distribution, we call this the IID random code book, because each code word is sampled from this IID input distributions, and also we obtain this IID random code book induced density at the output, where we put n everywhere because it's an n-shot case. Okay, then here, and the cobalt size in the N-short case is has this rate R. Then we want to ask how fast does this cobalt random IID random cobalt induced density converge to the true Roby tensor N in the Bragg length N? So that's our questions. Okay, and we will consider the second input distribution, which is the constant composition input distribution. This is a uniform input distribution on a sequence of Xn who has empirical distribution as the same as this Px. And then the corresponding output distribution is Roby N, and this is no longer a tensor product state. And we put this accent here to denote it is a constant composition input distribution. A minute. It stops. Okay, sorry, give me a second. My slides stop sharing, so let me share my slides again. Okay, sorry for the maybe some technical issues. Okay, so is it all good now? Okay.
We don't see slides.
Oh, okay, you don't see the slides. Okay, let me show it again. Sorry, there must be some problems. How about now? No?
Not yet.
Not yet. I don't know what happened.
No? Okay, let me share again.
Are you doing shared desktop?
Yeah.
Sorry, we still don't see it.
Okay. Sorry for.
Maybe some problem. So maybe you can send your presentation file to me, so then I can open instead of you.
Okay. So let me just log out and log in again to see if.
Log in again.
We see now, but I don't think we hear you.
Okay, good. Sorry. Okay, let me continue. Okay, so we are talking about the constant composition codes, and then it's not tensor products again, but we can also consider those true density output, and then we will use such constant composition input. We call this the constant composition random cobooks, and then we will get this constant composition random cobook induced output densities. And again, we want to ask for each cobook size rate, and then how fast does this cobook induced state converge to the true output state. But now this is not tensor product again. Okay, let me give some brief literature review. Okay, so this problem was first studied by Weiner in a classical case, and he called this the soft covering in a classical setting. And then Han and Verdu also studied this problem, but they used the optimal cobook. They call this the channel resolvability, and the soft covering is an achievability for channel resolvability. Let's show that when the rate of the cobook size is larger than the mutual information, then they show that the expected total variation distance will vanish asymptotically, not exponentially. And they also provide a weak converse for some spatial. They consider the channel with full rank. They consider it full rank channels. Okay, so they call this, they study this approximation of output statistics. So that's why they consider these problems. Since then, there are many applications of the soft covering afterwards, but they are all classical information theory works. And as for the one-shot case, I want to remark that Hayashi-san proposed a one-shot of achievability bound. So an exponential convergence of the total variation distance in the classical case was obtained for rate larger than mutual information. Later, Kauf improved the achievable error exponent a bit by modifying Hayashi's one-shot bound. And then Yagli and Kauf, they obtained the optimal error exponent for both the IID random code books and constant composition random code books. Basically, they use method of types and a method in this paper. Okay, and Yasai in ISIT 2 years ago, he obtained exact polynomial prefactors. And for achievability, he also based on this the one-shot achievability bound proposed by Hayashi. So meaning that this bound is actually very, very strong. Okay, and actually there are very many distance measures being considered, relative entropy. There are many works consider this, and Renyi divergences and Wasserstein distance, and there's an E-gamma metric proposed by the Princeton group. Okay, and for rate smaller than mutual information, Watanabe and Hayashi-san obtained a strong converse property for channel resolvability and also second order rate, some exponential strong converse with certain symmetry assumptions on the classical channel. And Kauf also obtained a second order rate with some probabilistic argument. As for quantum, this soft covering problem was first studied by Aswid and Winter. They obtained this probability deviation bound, they call the operator Chernoff bound, where they also wanted to estimate the closeness between this code induced density and the true density. And here they consider the matrix order. So essentially, they consider the infinity norm as the error criterion in this operator Chernoff bound. Hayashi-san also studied this case in using quantum relative entropy. And in this work, we consider the uniform mixture at the channel output. And in this work, Hayashi-san consider that they can put different weights on code words. And I will refer the audience to Hayashi's book, section 9 for this quantum studies on these soft covering problems. Okay, so there have been many distance measures being used. So why do we consider a trace distance? So especially because of the Hall-level-Helstrom theorem, we would like the codebook induced density to be physically indistinguishable from the true rho B. So that's our motivation. Also, if you use other norms as the error criterion, but when you get back to the trace distance, there will be some dimension factor come out. So you can also use the operator Chernoff bound by Aswid and Winter, but this infinity norm, you will get a dimension factor. And when you use quantum relative entropy as the error criterion, then if you use the Pinsker inequality to get back to a trace distance, then the bound will not be very tight. So that's why in this work, we directly analyze the trace distance for this soft covering. Okay, let's go to our results. We first introduced two quantum Renyi divergences. The first one is the sandwich Renyi divergence. That's a well-known information quantity, and it can be written as this straightened alpha norm. And the second one is the Petz Renyi divergence. And for any input distribution and the CQ channel, we define a joint state as this. Then we can define two quantities, the sandwich Renyi information as this one, where we minimize the second argument, sigma b here, and also a slightly different quantity we call the Augustine information, where we want to compute the average of the sandwich Renyi divergence between the output and sigma b. Also consider variant Petz Renyi information, Augustine information, where we do not minimize the second argument. You may wonder, why do we consider this Augustine information? It is because that it appeared in some context of the constant composition codes, and we study those properties in this paper. And also Milan and Ogawa-san, they show that this sandwich Augustine information actually has some operational meaning. It equals to the strong converse exponent for classical quantum channel coding using constant composition codes. So actually this quantity is also very interesting. Okay, so with those expressions, our first result is to prove a one-shot error exponent. So given every input px in the CQ channel, for this, we obtain it, we write this CQ state. We prove that the expected trace distance has this exponential upper bound, where it is E star. The error exponent is defined in terms of the sandwich Renyi information. And this error exponent is positive if and only if log m, which is the log of size of the codebook, is strictly larger than the mutual information with respect to this CQ state. Okay, here I want to remark that in the classical setting, this sandwich information, this Renyi information does have a closed form expression, but for the sandwich one, there is no closed form expression, but we have an optimization algorithm to compute this guy. This is not so easy because it's not just the standard gradient descent with fixed step size, because this Renyi divergence has very spatial structure. So we need more method to compute these functions. Okay, so here, this is an one-shot error exponent for rate enough, then it's positive. What if the rate is lower than the mutual information? Then we prove a one-shot strong converse. We get a lower bound by at least 1 minus 4 times exponential decay. And this exponent is expressed in terms of the variant of Pet's Renyi information. And this exponent is positive if and only if log m is smaller than mutual information. Okay, in the IID asymptotic case, where the input distribution is tensor product, then just by the additivity of the sandwich Renyi information and Pet's Renyi divergence, then our result directly implies the exponential decay for both regions, for achievable rate region, where the rate is larger than mutual information, and also the achievable rate region. I want to remark that those results hold for any finite block length n, because we have a one-shot result, and by the additivity of the error exponents, we have any n results. And it also shows that mutual information is the minimum achievable rate, and also the strong converse rate. Okay, let's make an illustration here. So this is Roby tensor n is the target. Let's assume that it has full support without loss of generality. And every random channel outputs is like this. They might not have full support. Their eigenvectors might not commute with Roby tensor n. But if we draw enough samples, then the mixture of them, the channel ID channel output, will converge to our target Roby tensor n strongly. In the sense that the trace distance vanished in expectation, and the convergence is exponentially fast, and we give an achievable error exponent. Okay, so the same result holds for the constant composition code as well. Here we have this constant composition input and the corresponding output. We show that the expected trace distance also exponential decays for every n, and with these error exponents expressed in terms of the sandwich Augustine information, and for the strong converse with Pet's Renyi information. But here we have this polynomial k prefactor. This kp just depends on the support of the input size, because we will use some type decomposition. Okay, so we show similar result holds for the constant composition codes as well. Here I would like to give some remarks. So our one-shot achievability bound recovers Yasai's one-shot bound in the commuting case. And also our one-shot bound implies the asymptotic achievability by Yagli and Kopf. So that's why we believe that our error exponent is actually tight. But we use totally different approaches. That is, we use the complex non-interpolation techniques to prove our result. I will show the result proof later. And also, I want to remark that by Jensen's inequality and concavity of log, the error exponent using constant composition code is actually larger than that using the random ID random code books. So using constant composition codes actually has some advantages for this alpha larger than 1. Okay, so that's the large diffusion case, meaning that the rate is constant away from mutual information. We obtain the exponential convergence. And for the moderate diffusion regime, meaning that the rate of the codebook approaches the mutual information at the speed of an. This an approaches to 0, but not faster than 1 over square root of n. In this case, because we want the rate to be as small as possible, tending to mutual information. In this case, we also show that the expected trace distance vanish but sub-exponentially for both the random ID random codebooks and the constant composition codebooks. Okay, here is an illustration. The x-axis is the rate of codebook. The y-axis is the trace distance. And then we can, because our results one shot, we can evaluate every n shot case. And then when n goes to large, then we obtain the large deviation result, meaning that exponential decay for the achievable rate region and the strong converse region. And we also show the moderate deviation region when the rate approaches the fundamental limit. The error also vanished. You may have seen this figure, similar figure as Christoph Trapp yesterday, but note that this figure is mirrored to the classical channel coding because right now the achievable rate region is to the right of the fundamental limit, whereas in the secret channel coding part, the achievable rate is the left part. So this self covering is kind of dual to a secret channel coding. And this is the contribution of this work, the moderate deviation and large deviation. And in our follow-ups, we also consider small deviation region where we fix that epsilon error, and then we show that the rate converges to the mutual information at a speed of 1 over square root n. But we use different techniques because small deviation and large deviation, they are not the same regimes. Okay, so let me quickly go to our proof ideas. Our point is a functional perspective from the non-commutative LP space. So for any operator valued function from some sample space to the bounded operators, we define the L alpha as alpha norm, which we take the as certain alpha norm on the operators, and then we take expectation raised to the alpha and take expectation. Here the probability is just the input distribution in our case, and take 1 over alpha. Okay, but in our code book, we have m code words, and they are all random variables. So essentially, we have m probability space. So we introduce this map pi n, which is an embedding from the original probability space to the m-fold probability space because we have m code words. They are identical. They are pairwise independent. So each pi m is an embedding to evaluate it on the mth probability space. And also we introduce the upright e, which is a constant valued random variable. Then the mixture of them to the e is like a empirical average, the difference between the empirical average to the ensemble average. We denote this as a theta, which is a linear operation acting on the operator valued function. We will use this notation to evaluate the components of covering problems. Okay, also note that the composition of secret channel with the random codes can be viewed as an operator value function from the sample space to the density operator space. So we can express this expected trace distance as the L1 as 1 norm on this linear operation theta acting on the operator valued function, which embodies the random codes and also the secret channel. Okay, so we want to upper bound this guy. Using holders inequality, we can move from the L1 S1 space to the L alpha S alpha space with some sandwich sigma b density operators, and this sigma b can be arbitrary, so we can obtain this for free. So we have this L alpha S alpha norm on the theta acting on the state. In the end, we want to bound this term, so we bound this term by the L alpha S alpha norm on the input argument and the operator norm of this action. Okay, so let's see this brown part. If we take infimum over O sigma b, then this quantity is exactly exponential to the scaled sandwich raining information. And this guy can be called as the auxiliary function in terms of Gallagher's notation. So if we can get a good estimate of the operator norm of this green part, we are done. So for alpha being 1, we use triangle inequality to get a 2, and for alpha being 2, we use pairwise independence of the random codebooks and also the structure of the Hilbert space L2 S2 to obtain this 1 over square root m. Now we have controls of the boundaries. We just interpolate the boundaries to get this the contributions of the size. So we separate the contribution from states and also the actions, these mixtures, to different parts, and they both contribute to the error exponent. Okay, so it's about time. Let me get to conclusions. We obtained a one-shot achievability and strong converse part here. I didn't show the strong converse proof. It's in our paper. And for both the random ID and constant composition codebooks, our techniques is a known interpolation techniques. And I would like to remark that last year, Frederick, you please also use interpolation technique to obtain the exponent for privacy amplification and decoupling in terms of trace distance. We also use known interpolation, but our proof techniques are slightly different. Okay, so applications include wild type channel coding and only many covering type problems. And lastly, I want to remark that our result holds for infinite dimension Hilbert space as well, because in the proof, we didn't mention anything about the cardinality or the dimension of a Hilbert space. So our result actually very general. So we only use this known framework. Okay, it's about time. So thank you for your attention and sorry for the technical problem. Okay.
Thank you for a nice talk. So, Mark has one question. So,
yes, please.
Thanks for a very interesting talk. Can you go back to the slide where you showed the proof?
Yes.
With the
this slides.
This one, yeah, this is all very interesting. And for the first inequality, you applied Holder's inequality.
Exactly.
What I'm used to seeing is you have the upper bound is in terms of like an alpha norm and a beta norm, where 1 over alpha plus 1 over beta equals 1. So am I missing something?
Here I simplify something. There should be this guy times another guy, but another guy is just 1 because it's 1. It's 1 because here sigma b has to be density. So taking some power of density and taking trace is 1.
Okay, thank you.
Here I simplify something. Thanks for this question.
Sure.
So other question? So I have one question and comment. So
yes.
Usually, you show the several regime. One is the large deviation, and the second is the moderate deviation, and the third one is small deviation.
Yes.
But sometimes small deviation is called central limit regime, central CLT regime. So, and then so small deviation, not small, moderate deviation case somehow almost no variety. So there is some linear, some exponential linear scale. So the coefficient is only the somehow variance. So this is somehow very simple situation. But in the case of large deviation, we have a more complicated situation. We need to consider something, a kind of Legendre transform of Renyi divergence, Renyi quantity. But that kind of Renyi quantity is not unique. There is so many kinds of Renyi quantity. So depending on the problem, we need to find a good Renyi quantity.
Yes.
So in this sense, this area has, this regime has much variety, so more interesting topic. And how about the small deviation case? Mainly, we have a central limit theorem, so then we have a Gaussian distribution.
Yes.
But yesterday's talk and my old paper discussed yesterday Chub's talk. At that time, his result is related to my old result, and in that case, that small deviation regime has a somehow Gaussian distribution.
Yes.
No, not Gaussian. Not
okay. Difference between Gaussian. Yeah.
Different. Yeah. So, did you have some experience found the small deviation case, but the distribution is not Gaussian?
That's very interesting. Okay. Okay. So I do think this quantum soft covering has a very similar picture as the classical quantum channel coding, and we already know the second order asymptotics for at least classical quantum channel coding. So in this work we obtain the Gaussian as the central in the second order terms. As for which tasks which do not have Gaussian, I would say maybe wild type channels, because we have the difference of 2 terms from the Bob part and also the if part. So, okay, but in the classical case, if we consider multivariate central limit, multivariate variation bound, we can obtain also in this Gaussian normal distribution expressions. But if we don't use that, like we only want to consider the rate, and we don't want to use the multivariate variation bound, and we will have to deal with the difference between two second order terms. One came from the Bob part, the transmission part, and one from the if part. So there will be a difference between two second order terms. That's I can.
So then conclusion, the second order is Gaussian or different distribution.
Yes, in wild type channels.
Yeah.
But in this case, we only have the CQ channels, so everything is kind of simple. Everything can be so we only have this phi rho. Okay, so in the moderate deviation, we also have this phi part, this variant quantum information variance part here.
We have only one coefficient, so
yeah. So they also
this.
Yeah.
So it's different. I see.
Yeah, but for different corpus, because we actually have two different definitions.
Sometimes we have two kinds of barriers in the case of channel coding.
Yeah, exactly. Like expectation inside or outside this information. Yeah, but in this case, it's basically.
If you consider channel and source joint coding, in that case, even in the second order, we don't have Gaussian. We have a slightly different distribution.
In which problems?
Channel and source and channel joint coding.
Oh, okay. For that, okay, because for source channel coding, we have the contributions from the channel part and also from the side information part. So essentially, we have sum of two second order terms. So yeah, yes, it's very similar to the wild type channel coding I just mentioned before, because in the wild channel coding part, we have the difference between two second order terms. But in the joint source channel coding case, we'll have the sum of two different second order terms, one from the channel part, one from the source part. So yeah, I agree in that.
So in that case, I already have some results. So in that case, we have a different distribution.
Yeah, I can.
So the state conversion case, we have that kind of different distribution, and also joint coding. So channel source and channel joint coding, we have different distribution. In my
that would be more complicated because now we have two sources.
Problem usually we have only Gaussian distribution, very simple.
Yeah, it depends on because here we have just raw, but in joint source channel coding we have another contribution, we have another state. So we have to consider that part, the contribution of the second order asymptotics of that part. So that would be more complicated. Yeah, I agree.
Thank you. So maybe we have time. So maybe
okay. We can talk about this later.
So thank you very much.
Thank you.
So maybe next speaker is please prepare next speaker. So Yon Shen Yao, could you prepare? Oh, okay. But wait. Please close your thread now. Sorry. I want to check the third speaker slide. So Michael Xuan Hao. Michael Xuan Hao. Please close. Please close. Yeah. Please close your thread now. Sorry. I want to check another one first. Please close.
I'll go. Okay.
Hey, is anyone trying to talk to me? What is going on?
I think Masahito wants Yongsheng to unshare his screen and for Michael to test his slides.
Oh,
Okay.
I find it very confusing. So should I do that right now?
Please test your slides.
Yes.
So please test so because you mentioned that you have some trouble, so
Yes.
I'm afraid. Okay, that's nice.
Is it working?
Looks good.
Okay, thanks.
Actually, I'm not so sure because not enough information is
So
being
please close,
displayed on my
please.
screen.
It looks
Okay.
good.
Okay,
Okay,
please,
it looks
now, please start.
Okay, sure. Thanks.
Yeah.
Yongsheng, please share your
Okay,
slides
okay.
and
Now,
start your talk.
start. Okay, and the next speaker is Yuanxin Yao. The title of his talk is Reliability Functions of Quantum Information Decoupling and Channel Simulation. This is joint work with Kari. Please start.
Thanks to the organizer for giving me the chance to give this talk. This is a joint work with my
Please,
supervisor.
full screen, full screen, full screen.
Can you hear me?
Please
Full
make your slides full screen.
Uh,
Let
my
me
slide
talk,
is in full screen mode.
If you could go to presentation mode for your slides.
let me talk to 永生，
Okay.
叫你全屏，
这个已经全屏了。
我们没看到全屏。
Okay.
Thank you. Perfect.
Can I start?
Yes,
Okay,
please.
start.
This is a joint work with my supervisor, Curly. This is the outline of this talk. I first introduced the definition of the reliability function in classical information theory, some quantum entropies and related information dielectrics. Then I will introduce our main results, the reliability function for quantum information decoupling and its application to quantum channel simulation. Now I will introduce the concept of the reliability function by using the classical channel coding as an example. As one of the most important results in classical information theory, Shannon second theorem states that the sender can transmit classical message to the receiver with asymptotically vanishing error if and only if the transmission rate is below the channel capacity. Although Shannon's second theorem can ensure reliable communication asymptotically, we can only get finite channels in realistic setting. So determining the form of the optimal error when the number of channels are finite is more meaningful. The reliability function of a classical channel is defined as the exact exponential rate under which the optimal error among all communication schemes with a fixed rate tends to zero. If we can derive the expression for the reliability function, we will calculate the approximation of the optimal error when it is sufficiently large. Determining the reliability function of a classical channel has a long history. This problem has not been solved until now. Here are two important progress. Fano and Gallagher derived a lower bound by using an elegant random coding technique. Then Shannon, Gallagher, and Burley-Camp derived an upper bound, which is called the sphere packing bound now. Comparing the expressions and the figures of these two bounds, we can find that the lower bound matches the upper bound when the transmission rate is larger than a critical value. So we can get the exact expression for the reliability function in the high rate region. However, when the transmission rate is below the critical value, neither the random coding bound nor the sphere packing bound is the correct expression for it. And determining the expression in this interval is still an important open question. As for the reliability functions of quantum information tasks, we don't know too much. For partial results, see the following paper. Now I will introduce some quantum entropies and related information darages. In quantum information theory, the quantum states are the positive semi-definite operators with trace 1. The phenomenal entropy of a quantum state is the generalization of the classical Shannon entropy defined for a probability distribution. The conditional entropy under the mutual information for a bipartite state are defined based on the phenomenal entropy, and both of them can be expressed in the form of Yumigaki relative entropy. The classical running relative entropy is an important quantity in classical information theory. There are various quantum generalizations for it. The most important among these are the savage running relative entropy and the Pace running relative entropy. The savage running relative entropy was first put forward in these two papers. It has nice properties and operational meanings, especially in characterizing the strong reverse exponent for quantum tasks. Based on the savage running darages, we can define the savage running mutual information for a bipartite state and a quantum channel. These two quantities are important for characterizing the reliability function for quantum information decoupling and quantum channel simulation. The above introduction is our motivation and some preliminaries. Now I'm going to introduce our main results. The task we studied is quantum information decoupling. Decoupling means that Alice and a referee share a bipartite state. Alice first applies a unitary operation to her part and discard a subsystem to erase the correlation between the remaining system and the reference system. In order to do better, Alice can attach a catalytic state and at the initial step and repeat the decoupling processes stated above to erase the correlation. The quantum information decoupling is an important task in quantum information theory. It also has applications in quantum thermodynamics, statistical physics, and black hole physics. For bipartite state and a catalytic decoupling scheme consisting of a unitary operation U and a catalytic state, the performance of this decoupling scheme is characterized by the minimal purified distance between the final state and the ideal product states. For a fixed cost rate R, the one-shot optimal performance is defined as the optimal performance among all decoupling schemes with cost less than R. And the reliability function for quantum information decoupling is defined as the exact rate of exponential convergence under which the optimal performance among all decoupling schemes with cost less than R tends to 0. In our work, we first derive an upper bound for the one-shot optimal performance. The main tool we used is the convex splitting lemma. This technique was put forward by Aishu et al. based on their proof, we can upper bound this relative entropy by this formula, which is characterized by the salvaged running relative entropy. From this lemma, we can construct a catalytic decoupling scheme as follows. By simple calculation, the performance of this catalytic decoupling scheme can be upper bounded by this formula. So from this one-shot upper bound, we can easily get a lower bound for the reliability function. Next, we derive a lower bound for the one-shot optimal performance. The smooth quantity for max information is crucial in the derivation. This smooth quantity can be regarded as the inverse function of the smooth max information. We have proved the one-shot optimal performance has the smooth quantity as its lower bound. And for n copies of row AB, this smooth quantity decays to 0 with this exponential rate. The main methods we used to prove this conclusion are the Gartner-Ellis theorem of large deviation theory and the exponent is smoothing the max relative entropy. So from this conclusion and this one-shot lower bound, we can directly get a upper bound for the reliability function. We summarize the lower bound and the upper bound here. Both of them are characterized by the salvaged mutual information of the bipartite state, and they are in a similar form. When the cost rate is below a critical value, the lower bound will match the upper bound. So in the low rate region, we can get the exact expression of the reliability function. Next, I will introduce the application of the above results to quantum channel simulation. Every quantum channel has a Stein-Spreng representation. That is, we can first apply isometry operation to the initial state and discard the environment system to recover the action of the noisy quantum channel. The quantum channel simulation is a fundamental and important task in quantum information theory. In the early setting, we want to transmit as much ideal information as possible by using as few noisy quantum channels as possible. The maximal rate of ideal information that the noisy quantum channel reliably transmit is defined as the channel capacity. According to the type of transmitted information and the results shared by the communication parties, there are various forms of quantum channel capacities, including classical capacity, private classical capacity, quantum capacity, and entanglement assisted classical quantum capacity. The formulas of most quantum channel capacities are in the regularized form, so it's hard to calculate its volume. The formula of entanglement assisted classical capacity is the only one in the single letter form found so far. It's also regarded as the most natural quantum generalization of the classical channel coding problem. Complementary to the entanglement-assisted classical communication, the entanglement-assisted quantum channel simulation considers the minimal rate of classical communication in order to simulate multiple copies of quantum channels. The quantum reverse Scheiner theorem states that for asymptotically reliable simulation, an amount of classical communication equals to the entanglement-assisted classical capacity is necessary and sufficient. Although this theorem provides a sharp threshold for reliable simulation, it can't answer the question regarding how fast the perfect simulation can be approached. This is the goal pursued by the study of reliability function. In our work, we use the purified distance between two quantum channels to characterize the performance of a simulation scheme. The reliability function is defined as the exact rate of exponential convergence under which the optimal performance towards to 0. We also derived a lower bound and upper bound for the reliability function. Both of them are characterized by the salvaged Rani mutual information for a quantum channel. When the cost rate is below a critical value, the lower bound matches the upper bound. So in the lower region, we also can get the exact expression for the reliability function. In our proof, we first use the technique of quantum definite reduction, which states the simulation is good for all input state, if and only if it's good for a special symmetric pure state. This technique was first put it forward in this paper. However, in that paper, they used the trace norm distance as the measure, and we extend this technique to purified distance. That we use the Stasberry isometry of the simulated channel to act on the symmetric pure state to get a tripartite pure state, and use the catalytic decoupling scheme stated before to construct a state splitting protocol, and use this protocol to transmit the system Bn to the receiver. Finally, discard the environment system to finish the simulation. The performance of this simulation decays to 0 with the desired lower bound as the exponential rate. And in these processes, we use the additivity of channel running mutual information. Finally, I give some summaries and open questions. In our work, we started the complete characterization of the reliability functions for quantum information tasks. The results are given in terms of the salvaged running divergence, providing it with operational meanings in characterizing how fast the performance of quantum information tasks approach the perfect for the first time. See also yesterday's talk by my supervisor colleague. Especially, we gave an operational meaning to the channel salvaged running mutual information, justifying its well definition. There are some left open questions in our work. The first question is determining the reliability functions above the critical points. The second is study the reliability functions of other quantum information tasks. And in this process, we might find more types of running information damages. That's all my talk. Thank you for your attention.
Thank you for the talk. Is there any comment or question?
Hi, Yongsheng. I have maybe a comment.
Marco, so please.
Yes, so thanks a lot for the talk. This is very interesting work, and I think somewhat more complex than what we did. We looked, however, at the moderate deviation case for channel simulation in a recent work with Ramakrishnan et al. And Mario Berta as well on it. And I think we did some of the similar things. So we also had to do this post-selection in purified distance, for example, because we use this strong duality between the channel simulation and channel coding. And then you kind of need to go via purified distance. So maybe there's some overlap, but we didn't look at reliability. So, but in any case, a very nice talk and nice work. I can send you the reference later.
Oh, thank you.
Thank you, comment. Other comment or question? Hao Jian also, please.
Yes. Thank you, Yongsheng, for this very nice talk. I have some questions. So you use purified distance and derive the error exponent. Did you consider the infidelity as the error criterion? That is the 1 minus fidelity?
Fidelity, maybe fidelity is equivalent to the purified distance.
Okay, so they have the same error exponent, the purified distance, or infidelity, they have the same error exponent. That's what you meant?
Yes.
Okay, thank you. Yeah, and my second question is that because you use the large deviation techniques, and there's a paper by me and Macron and Michel with derive the refined severe packing bond. We also use some large deviation techniques, and we obtain the improved polynomial prefactors. Is it possible to get similar result? I mean, the polynomial prefactors in your upper bound to the reliability functions?
You mean this?
Oh no, the other way, because this one is achievability. I mean the other one, the other direction, using the smooth max. Here, this one.
I haven't considered this problem. I think it's a nice question. Maybe we can improve the
polynomial prefactor.
Yes.
Yeah. Okay. Great. Okay. Sorry, I have a last question. So for quantum information decoupling, you still need catalytic decoupling, right? So what's the difficulty to remove this condition of using catalytic decoupling?
Without the catalytic.
Yeah, exactly. Yeah.
Because our technical our tool use the convex splitting lemma.
Yes.
And from this lemma we must need a catalytic state.
Okay. So the problem is here. Okay. This is a very interesting, very nice topic and works. So very nice work. Okay. Thank you very much for your answers.
Thank you.
So thank you, nice talk, and for a good question. So is there any question or comment? So now we have time. So I want to move to the next session. Thank you very much. So could you close your slide?
Okay.
So then please prepare next speaker, Mikhail. How? Mikhail Shu Kao.
Hello. Thanks,
Hello.
Dr. Hayashi.
Yes.
Let me share my screen.
Yes, please. Okay.
Yeah, it works.
Okay, please start. So the final speaker of this session is Mikhail Kao. The title of his talk is Challenge Simulation Finite Block Length and Broadcast Challenge. This is joint work with Navenish Ramakrisham, Mario Belta, and Marco Tomameteo. Please start.
Thanks, Dr. Hayashi. Thank everyone for coming to today's talk. So tonight, I'm going to talk about the finite block length channel simulation. My name is Dr. Michael Cao, and this is joint work with Navnis, Mario, and Marco. So the question or the setup is we consider the classical, everything is classical in this talk, unlike the previous two talks. Wait, I didn't even make sure that my voice can be heard. Is it operational? Okay, I just assume it works.
Yes, yes.
Okay, thanks. Okay, so the problem setup is we consider a problem of simulating a target channel, say W. Wait. Then and with the assistance of shared randomness, where in this diagram, S is a shared randomness, and you have encoder ES and decoder DS, and you map the input to a certain message, and then you decode it. The target is to have your this effective joint distribution to be epsilon close to a certain distribution, where a certain distribution is derived from a specific channel W. And however, the PX is not controlled by you. And what you want is this thing to be small in terms of total variational distance for all input distributions. And wait. So we're interested in finding the smallest alphabet for M, such that there exists some encoder, decoder, and shared randomness tuple satisfying the distance constraints. And that is called the epsilon cost of the task of channel simulation. So this is related to the notion of strong coordination, in which case PX, the input distribution, is actually known beforehand. In that case, you try to reconstruct the joint distribution PXY, where despite knowing the input distribution, but the input distribution symbol is not controlled by you. Whereas in this case, in channel simulation, you need to recover the joint distribution, but you also need to do so without the knowledge of the input distribution in a sort of universal way. Also, the problem of channel simulation and channel coding are kind of dual problem of each other. So the coding problem essentially is using, say, your resource channel W to simulate a perfect channel. You simulate R copy of the perfect channel, where usually I is called the rate of your communication. Then reversely, you could use those number of perfect channels to simulate certain numbers of the original channel. So one thing you can make sure is the ratio, it will be smaller or equal to 1, because you cannot create more resource by not introducing additional resources. Also, this problem is directly related to the reverse Shannon theorem. It is in the case of reverse Shannon theorem, it's actually considering the problem of channel simulation in an asymptotic manner. But in today's talk, we are talking about the one-shot and finite block length situation. So the main results, I'll briefly go through the main results of our work, and then I will only talk about some of them in details. So we have one-shot achievability and converse, which in terms of smooth max information, where the smooth max information, we define it in terms of partial smooth max divergence, which is defined in terms as using a max divergence, but you just draw a ball, epsilon ball around the joint distribution, but you fix the px. I mean, that's why it's called partial. And we can see that, I mean, we found that the for a given tolerance epsilon, the log of the minimum message size, you need it at least to be the I max epsilon. And for achievability, we also have an achievability result that you at most only need I max epsilon minus delta plus certain Fung terms. Then, shouldn't this be 2 slides? Oh, that's a latex error. So we also have the second order expansion for simulating, say, n copies. Sorry, I'm not sure where the slide number is. Okay, for second order expansion, we consider simulating n copies of the channel DMC W within a TVD of epsilon. In that case, we know the first order term is channel capacity, and the second order terms in terms of square root of n times certain constant, and the constant is in terms of the epsilon channel dispersion. This is very similar to the result of channel coding, the result of second order result of the channel coding. In that case, you will have, this term will be same, and then the second term will be epsilon. But there will be a gap between the channel simulation and channel coding on second order. Therefore, we already know that one will not have channel interconversion on second order if you lose something. In the case when the epsilon channel divergence is strictly larger than 0, we also have a third order upper and lower bounds. They don't match currently, and we are still working on that. So the third order terms is in terms of log n. We know it's between plus and minus log n. Then there's a constant term after it. So we also did the considering situation with moderate deviation errors, where the epsilon, the tolerance we allowed, will tend to 0 exponentially with respect to 2 to the power n an squared, where an is a moderate sequence. It tends to 0, but n times an squared tends to infinity. In this case, we know that in a similar notion of the second order, you will have the multiplicative constant as square root of 2 to the power v max. Then the remaining will be negligible compared to an. So as a second part of our result, we were able to connect the problem of non-signaling channel simulation to the random assisted channel simulation. In particular, the non-signaling channel simulation cost can be written as a linear program. And we are able to show this linear program will exactly have this solution, which is the I epsilon max, meaning that non-signaling channel simulation will need the lower bound we see on the last page for the random assist channel simulation. Of course, this also provide a linear program for us to compute the lower bound of the previous page. And in this case, we have some numerics. In this specific figure, we were considering a binary symmetric channel. I forgot the crossover probability. But I remember epsilon is 1/5, the tolerance. So we were also able to generalize our result to broadcast channels. For the situation with two receivers, this is the diagram on the setup for for the channel simulation. In this case, we have two shared randomness instead of a shared randomness for everyone. That one would be stronger. Of course, that would also work. And the task is also to have the joint distribution to be close. And one is the result of the channel, and the other is the result of your protocol. And you want them to be close regardless of the input distribution and without knowing the input distribution. So we have the inner and outer bound to the simulation region in terms of spectrum divergence. We are defining spectrum divergence slightly different by requiring A to be non-negative. And asymptotically, if you consider as n copies of simulating n copies of broadcast channel, then we consider the rate of such simulation and let epsilon, the tolerance, tend to 0. We end up having the region of the simulation region, a simulation rate region, sorry. And in this case, on the left-hand side, it is an example of a simulation region of degraded binary symmetric channel. It means like you have two binary symmetric channel. You just fit the output of one as an input to the second, and then you have one input and two output, like X, Y1, then Y1 to Y2. And on the right-hand side, it is the simulation region of three binary symmetric channel linked to each other, linked to the other. It is still called degraded binary symmetric channel. So you have X, Y1, then Y1 to Y2, then Y2 to Y3. So this generalized to k-partite broadcast channels, where you will have a similar bound here. Here, C tilde is the supermem over all input distribution of the common information, defined like this. So C tilde in this specific example, C tilde part is responsible for this diagonal cut. So for the technical part of today's talk, I'm only going to talk about the one-shot result and the asymptotic analysis due to time constraints. We are finishing an archive draft. It will be ready soon, at least on the technical part already. So the achievability part first. Achievability part of the result depends on, we use the convex split lemma. We recently realized there are other better, potentially better method. So the convex split lemma, what it says is that if you have a joint distribution over X and Y, and let Q be any, it's important, let Q be any distribution over the output alphabet Y, and given any epsilon and delta, and then if M is large enough, larger than this this value, then if you let J be a uniform distributed among 1 up to M, and condition on J, you have X and M copies of M number of Y distributed like X and Yj, the J's one are distributed according to the joint distribution, and remaining one just copy IID copy of Q. Then this distribution will be very close to the distribution that you have Px, but everybody else is just Q. So you don't necessarily, in the second one here, you don't have the information on information on the on Y, the original Y. So what we can use this convex split lemma to cook up a protocol for channel simulation, and it goes like this. So say let Px prime Y prime be the optimal PMF for Dmax. And in this case, Dmax means that this Px prime Y prime is close to Pxy, and Px prime is exactly same as Px. And their log likelihood ratio is smaller or equal to this number. Okay, so we can construct random variables j and x prime and all these y's from this x prime and y prime on the as illustrated on the previous page. So we know that using property of the channel of the information divergence, you can simply write out that the KL divergence between this constructed random variables without j and the situation that all these y's are independent is smaller or equal to this one. This is just a property of KL divergence, which is smaller than this one, which is nothing special. Then here, this is because of the here's because of the previous lemma. Then sorry, actually I'm trying to I confused two slides. This is the earlier slide, so this one is proving the lemma one. I apologize. So yes, we constructed a random variable like this. Then we use the property of the KL divergence, and we can show that they are close. Yes. So using this lemma, the protocol goes like we chose specific Q. Then if it is close, then we can use the previous lemma to show that the constructed J prime up to Y primes, they're close to the target protocol. And the proof goes exactly okay. This is what I have been trying to talk about in the previous minute. Okay, so for the converse, the converse depends on the properties of the max information and its relationships to Dmax and partial smooth Dmax. So to prove the converse, we consider, say, xy to be the distribution generated by the protocol. Then by lockability, we know that first we know that log m equals Imax of x and s. S is the shear randomness and plus log m. This is because log m is simply not here. This part, the Imax x and s is simply 0 because they're not they're independent. Then this is greater or larger than Imax x and ms as a result of lockability. Then using data processing inequality, we can replace ms by y. Then the remaining part is just to expand this Imax considering a definition of the smooth divergence. Firstly, it is defined, Imax xy is defined like this. This is infimum over Q. Then this is again a definition of Dmax. Then we swap, we add a supremum over px instead of max x. In particular, in this case, notice that this expression actually has nothing to do with px. We can just add px on the denominator and numerator. So this is greater larger than the partial smooth Dmax because of the definition. And now for the asymptotic part or the first order part, we are able to show that okay, for the achievability bound, we're able to show that this is smaller. You need at most capacity amount of bits. Firstly, you apply the previous result for n copies of W, and you just plug it in, and you have the first line. Then you convert the whole thing to the spectrum divergence. There's the relationship between spectrum divergence and the max divergence. And yes, and we used equation 9, inequality 9, which is a modified version of the theorem 9 from this paper, slightly modified. Then, okay. Then we use the, I think this is called quasi-convexity of the spectrum divergence. And then one can, okay, wait, okay. And here we chose a specific because this works for all QY. Is it because it's smaller or equal to an infimum of all QYs? We chose a very specific QY and plug it in. And where QY is the average over all input types, the average of the output distribution with respect to all input types. And you directly plug in QY, you have this part. And so it's just directly plug in. Then we can, instead of consider all the types lambda, we can just pick a specific lambda, which is the type of the sequence X. That when you do the supremum over sequence X, we just replace that lambda by the type of sequence X, and then that would give that additional term that is probability of sequence the type respect of the sequence X happening. Take a log, and in this case, the first part, then we expand it. We expand the first part. That is the expansion of the spectrum divergence, where V is the divergence variance, variance of the information divergence. So then, okay. Then if you look at the first part, we have sum over I, that's n copies of them, but X is here. So this is an equivalent just by counting. You can recover f the frequency of fx. So by counting, we have the first part being the mutual information, and we just copy down the second part. And all the terms besides this term will tend to 0, and this term is upper bounded by the capacity. Okay, so that is the proof of the first order result. As for the converse part, we start with the previous one-shot result and plug in the n-fold of W. Then again, we convert it to the spectrum divergence using a different lemma. And we're okay, yes, lemma 7 is here. Then we do have an infimum over Qy. Here, yes. And this can be thrown away by adding additional term. And without Qy, just by the famous information spectrum method, we know the first part will tend to the capacity of the channel. And second part will tend to 0, which is kind of straightforward here. So combining the two previous results, we know the first order cost for channel simulation is capacity of the channel. So as a summary, we give the upper and lower bound, one-shot upper and lower bound to the channel simulation cost in terms of the smooth max information, smooth max mutual information of the channel. The achievability part is a result of the convex split lemma. And the converse part is a result of a lockability and data processing inequality of Imax, among other things. So we know asymptotically the cost coincides with the capacity of the channel. So, and this implies the channel interconversion on the first order. That's the technical part I talked about. There are other things I think that's noteworthy, but I haven't talked about them. That is, we also know the second order behave like this, and okay, actually we know the third order behave like this when the channel divergence. Okay, this is type 1. This should be larger than 0. When the channel dispersion is greater than 0, and when it is 0, we have a simpler form. So this is interesting because this implies that channel interconversion won't work on second order. Okay, that's all for my talk. Any questions?
Okay, thank you for the talk. Is there any question or comment?
Hello, Haochen.
Yes, yes.
Please, Hao Chen.
Hi, Michael. Thank you for this nice talk. Nice to see you again. Okay, so I have two questions. The first one is that, do you know the first order of simulation of broadcast channel without degradability? Without, because in your talk, I remember that you consider degradable broadcast channel, right?
Actually, we consider.
Oh no.
We consider general broadcast.
General, okay.
That is only an example.
Oh, okay, that's interesting because in the
this works for all broadcast channels.
Not just
for all 1K broadcast channel, you have one sender.
Yeah, we can just consider two binary case, R1 and R2 case. But here, in this formulation, it seems that it's a degraded broadcast channel, right? But your result actually beyond that.
The examples, numerical result examples are degraded broadcast channel.
Okay, but your result extend to the non-degraded one.
Actually, we started with non-degraded one. We just finally use a degraded broadcast channel for numerics. Okay.
So my question is that in broadcast channel coding, not simulation, broadcast channel coding, I think the first order, the optimal rate region is unknown, right?
Yes.
So
we don't know how to actually. That's why it's hard to say that. But actually, we know the interconversion would work.
Okay, that's interesting.
So hi, Hao Chung. So Michael didn't want to make our result look too interesting, so he didn't mention it. But actually, the interesting thing is that in simulation we have a nice closed form expression for the region, which we don't know
for channel coding.
Yeah, for the communication talk.
Wow, that's very interesting.
Communication?
Yeah. Okay. My second question is that you use the trace distance partial smooth Dmax, and you relate it to the back to the information divergence. Does that hold for the quantum case as well? I saw in Marco's paper, the partially smooth information measures, there's a relation between this smooth Dmax in trace distance to the information spectrum divergence.
Oh,
does that hold
that
for
part.
Yeah.
That a lot of inequalities that we used, actually, they're from the quantum case. They also work in quantum case, including the partial smooth Imax and its relationship to
information
those
spectrum.
Dmax and DS.
Okay. Because for this trace distance smoothed quantity, it probably not an SDP. If you use purified distance as smoothing, then it's an SDP quantity. But for trace distance smooth quantity, probably I'm not sure, but probably it's not an SDP. So it's difficult to compute this Imax trace distance smooth quantity. It would be good to translate to other SDP quantities like information spectrum divergence or hypothesis testing divergence. So
I'm not sure of everything, but some of them will definitely work.
Okay.
Then at a lot of situations, you need to consider swapping the total variational distance to something other than a trace distance.
Okay, that's interesting. Okay, thank you.
It actually depends on how you prove those lemmas.
Yeah, that's very tricky.
Classroom cases are particularly easier to prove those lemmas.
Yes. But I'm not sure for a quantum case. Do we have those nice relations between those quantities? I'm not sure. So that's why I'm asking. Yeah, so maybe you already have some results. Okay, let's talk at some point. Thank you very much.
Thanks.
Okay, other question or comment? So I have one question or comment. So in your initial part, you please back to the slide connection to some other works. This one contains some equation one. Yes. In this slide, you consider second problem. So you consider one-shot bound on the channel coding. So in this case, you consider ratio R epsilon as M epsilon. That ratio is definitely smaller than 1. Did you consider that ratio in this talk, in your research? Assumed behavior of this ratio.
Do you mean to ask, did I consider a situation that I replaced this perfect channel 1 with some other channel?
I'm asking this ratio, assumed behavior of ratio R epsilon and M epsilon. So you mentioned that this one is definitely smaller than 1. Of course, this is correct, but
they tend to actually if we consider situation with as many copies of W,
yes, of course,
as possible, then asymptotically, this term will tend to 1.
1.
I believe so. This is like
I think this is 0. This is 0.
This tend to 0. I thought for first order channel 1, let's call first order channel conversion.
Of course, first order is the same, but the second order is completely different. So I consider that problem in the case of entanglement distillation and data compression. Not channel coding, but similar problem. So the channel entanglement distillation and dilution, this is somehow dual problem. And also random number generation and data compression can be considered dual problem. In that problem, this kind of ratio should equal to 0 when epsilon equal to 0. I consider that problem. So because this kind of, if you consider second order expansion, that second order coefficient is completely opposite in that problem. First order is the same, but the second order coefficient is completely opposite.
Yes, the second order term has opposite. So when you do the one minus another, they actually add together.
Yes, so if epsilon and another epsilon plus equal to 1, maybe okay. But now you are consider
What I was thinking
go
about,
to 0, so
what I was thinking about, what if, is that, does it still tend to 0 even if you're we let the number of copies of W tends to infinity?
yeah, I think so. If both epsilon go to 0, this is 0, I think.
But I
If-
thought it's like, you need to
If
consider,
both epsilon, upper epsilon and the second epsilon, the sum of both epsilon equals to 1. So in that case, I think this is 1.
how about for fixed epsilon?
Because epsilon somehow, maybe if n go to infinity, maybe 0. Because second order is different. So
That would be very kind of surprising to me. I'm not sure about it. I
I
didn't.
already discussed that problem in several papers. So you can read my paper. I can send it to you.
It is very interesting.
Or maybe I can make a comment. So I think it's just a different formulation. Michael, we can look at the paper by Professor Masahito Hayashi, and then it's a slightly different formulation. And in that case, yeah, you can show the irreversibility, but
Yes,
it also follows from our arguments. Yeah.
Okay. Any other questions?
Other question or comment?
Very interesting result.
Lika, okay, please.
So, yeah, I'm interested if it shed some light to the quantum case.
Actually, the entirety of this project started from the project of quantum channel simulation. But there are just some other difficulties we encountered in that project. So we figured we should deal with the classical one first. So yes, a lot of the method used here are either inspired by some quantum literature, or they are just analogy to quantum results, especially those inequalities.
Okay, so sorry, maybe we already discussed enough time. So now I want to close this session. So thank you very much. So I already opened the breakout room, so you can discuss breakout room later. And after 20 minutes later, we start a music session. So so now I want to close today's